This is page 87. Yes, it is. And in fact, one of the ways that they came to know about compounds and the fact that they had simple whole number ratios of atoms in them is by using gases. Okay, and when we're talking about gases at S.T.P, the S stands for standard. The T stands for temperature. And the P stands for pressure. So we have S.T.P. Now, because we don't have a lot of time to spend on gases, we will not be looking at gases at other temperatures. But let's say that I had some gas and it was at standard temperature and pressure, and the standard temperature is 0 degrees Celsius, and the standard pressure is 1 atmosphere. Which can be abbreviated as 1 ATM, and that right there is S.T.P, standard temperature and pressure. Say I took that same gas, and let's say that the top part here, let's say there was a sliding piston, okay? What do you think would happen if I were to heat this up to a higher temperature? Remember, in here we've got gas molecules and they are bouncing around. What would happen if I heated the gas to a higher temperature, say 100 degrees? It would slide up. Why? What happens when we increase temperature? What happens to particles when we increase temperature? The particles move faster. They also have more energy, so they are colliding with the walls and that piston with more energy, and so they push upward. Does that make sense? Okay. So at 100 degrees Celsius, we would have a bigger volume because the piston would have slid upwards because the particles are now moving much, much faster and they're crashing into the wall a lot harder, okay? You're not actually responsible for knowing that in Chem 11, okay? But it's kind of nice to know that if the temperature gets higher, the gas gets bigger. Okay? So, once upon a time, there was a man named Monsieur Gay-Lussac, and he's one of those extraordinary figures in the history of science who could truly be called an adventurer. He was interested in lighter than air balloons, and in 1804, he made an ascent to 23,000 feet, an exploit that set altitude records for several decades. To better control lighter than air balloons, Gay-Lussac carried out several experiments on the properties of gases, and in 1808 he discovered the law of combining volumes, and that law of combining volumes is as follows. At a given temperature and pressure, the volumes of gases that react with one another, so the volumes that react with one another, are in ratios of small whole numbers. So you wouldn't have like 1 mole of chlorine, or sorry, 1 liter of chlorine reacting with 157,892 liters of hydrogen, because that's not nice whole number ratio. That's a nasty ratio, yes? So we want ratios of small whole number volumes. So let's take a look at one example that he did. So keeping here, remember he is keeping temperature constant, he's keeping pressure constant, because if we were to mess with the temperature, the volume would get bigger. If we mess with the pressure, essentially we're also messing with the volume, because when you increase pressure, you're squishing it. If you decrease pressure, you're making the container bigger, so it actually gets so there's less crashing into the walls. So he took some hydrogen gas and he reacted it with some chlorine gas, and he found that when he reacted 1 volume of hydrogen, it would react completely with 1 volume of chlorine, and you would get 2 volumes of hydrogen chloride. You didn't get 1.37 volumes of hydrogen chloride. You got 2 volumes. Nice whole number ratios. Now, years later, let's say, Signore Amadeo Avogadro, because he's Italian, interpreted Monsieur Gay-Lussac's observation by proposing what is now known as Avogadro's hypothesis. So Avogadro looked at Gay-Lussac's data, and he said equal volumes of gases. So if I have 1 volume of gas and 1 volume of gas, those are equal volumes of gases, contain equal numbers of particles, as long as they are at the same temperature and pressure. So equal volumes of gases contain equal numbers of molecules. So let's visualize this. What does this look like? If I have 1 volume of hydrogen, I can imagine that it's a little teeny tiny volume, okay? And it contains only 1 molecule. Yes? I have 1 volume of chlorine, and it contains 1 molecule. When those two combine, I end up with HCl, but I don't end up with 1 HCl particle. I end up with 2 HCl particles, and those 2 HCl particles take up 2 volumes. They don't take up 1 volume, they take up 2 volumes. The more gas you have, the more gas molecules you have, the larger the space it takes up, the larger the volume. So we have 2 molecules for that one. So this is Avogadro's hypothesis. 1 volume, if it's this volume, would contain 1 molecule. If I had 3 volumes of a gas for this particular model, I would have 3 molecules. Yes. Obviously, we're not dealing with 1 molecule, but there we are. Here's another one. We have 2 volumes of hydrogen, and this is actually really hard to read. I don't like this very well, so I'm going to write it again. I have 2 H2 molecules, and I add that to 1 O2 molecule, and you can see that the hydrogens get together with the oxygen, and these hydrogens get together with this oxygen. Yes, and we end up getting 2 water molecules. So 2 hydrogens, 2 volumes. 1 oxygen, 1 volume. 2 waters, 2 volumes. Okay. Now let's scale up and show more molecules, because normally we would have more than 1 molecule of each. Here we have 1, 2, 3, 4, 5, 6 molecules of H2. Here we have 3 molecules of O2. And here we have 1, 2, 3, 4, 5, 6 molecules of H2O. So for our molecules, we have a 6 to 3 to 6 ratio. Yes? 6 molecules to 3 molecules to 6 molecules. And if we simplify that ratio, what is that ratio simplified? 2 to 1 to 2. So our volume ratio is 2 to 1 to 2. So what that means is, if I have a balloon, and the balloons are all the same size, in other words, the same volume, what else are we keeping the same for each of these? We're keeping the same temperature. And there's a third thing that we're keeping the same. See if you can tell your partner. Pressure. Sorry. Pressure. No, sorry, I won't sing. Nobody wants to hear that. Okay, so we have the same volume, the same temperature, and the same pressure. So if I have helium in my balloon, how many helium particles do I have in there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 molecules. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9 molecules. And over here I have 9 molecules, because at the same temperature and pressure, it doesn't matter what gas we have. It doesn't matter if we have NH3, or if we have helium, or if we have oxygen. Those particles will take up the same amount of space. Now, it seems a little weird, because if you were to actually look at a helium molecule, helium would be about this big, and ammonia, NH3, would be about this big, right? So we would have a ammonia. Come here. So you can see that the ammonia particle is bigger than helium. Yes? However, gases are almost all empty space. The reason that the molecules look so big is because we have to draw them big enough so you can see them. How big would our helium actually be? It would actually be like smaller than that little dot there. Yes? So when we look at the volume of the gas, the volume of the particles actually does not contribute to it significantly. Okay. You don't really need to understand that, but that's what you would sort of look at if you were going deeper into the study of gases. Okay, the particles take up essentially no volume. The volume is almost all empty space. So it doesn't matter whether the particle is a little bit bigger, because this one would maybe be that big. Oh, look, they're still tiny compared with the actual empty space. The actual particles would be so much smaller than the drawings we have of them. Does that kind of make sense? Okay. Like I said, you don't really need to worry about that. But there we are. Now, to be honest with you, although we have drawn 9 molecules here, we are being told that there are 4 grams of helium in this container. I would like you to look on your periodic table and tell me what it means if I have 4 grams of helium. I have one what? I have 1 mole. If I have 4 grams of helium, I have 1 mole, because the molar mass of helium is 4 grams per mole. Now we are told that in our balloon here, we have 15 grams of NH3. I would like you to tell me what that tells us about the NH3. If we have 15 grams of NH3, how much NH3 do we have? I have 1 mole, because nitrogen has a molar mass of 14.0 grams per mole. Hydrogen, we have 3 of them, and each of them has a mass of 1.0 grams per mole, so we have 14. That's not right. What have I done? Nitrogen is 14. This should be 17. That should not say 15. That's a mistake, I think, unless I've done something wrong. Please let me know if I have. So the molar mass of ammonia is 17 grams per mole. That means we have 1 mole of NH3 in the balloon. I'm so sorry. Yeah, that's a typo. And I stole this image from somewhere. It's from a book. So the book has a mistake in it. Okay. Alrighty. Because you know I cannot draw like this. I don't have any talent with drawing programs or anything like that. Okay, so we have 1 mole of helium in this balloon. We have 1 mole of NH3 in that balloon, and it weighs a different amount because NH3 particles are heavier than helium particles. Yes? Now, oxygen, 32 grams. If we have O2 at 32 grams, how many moles of oxygen do we have? We have 1 mole of oxygen. So each of these balloons contains the same number of particles, 1 mole each. So not actually 9 molecules each, right? We just drew 9 because it fit nicely inside the balloons. Each balloon has 1 mole of gas, but they each weigh a different amount because some of the particles are heavier than others. Okay, each balloon contains 1 mole of particles. Some balloons weigh more because some particles are heavier. Are we making sense? Cool. So same volume, same temperature, same pressure. That means they will have the same number of molecules. Same volume, same temperature, same pressure. Therefore, we have the same number of molecules. Whose hypothesis is that? That's Avogadro's hypothesis. Okay, so that is Avogadro's hypothesis. How's that? Is it too small? Okay, so we can make measurements at any constant temperature and pressure. We can determine the number of molecules in a given volume. So for example, they did a bunch of experiments and they found that 22.4 liters of any gas at 0 degrees Celsius in 1 atmosphere. What is 0 degrees Celsius in 1 atmosphere? Tell your partner, what is that? What is 0 degrees Celsius and 1 atmosphere? That is standard. Standard what? Temperature and pressure. In other words, S.T.P. So at standard temperature and pressure, each of these is 22.4 liters. 22.4 liters. I know it labels it underneath, but sometimes, you notice better if I write it down. Okay, 22 point, each of those little things is 22.4 liters. We are all at 1 atmosphere. We're all at 0 degrees Celsius. So once again, what do we call that when it's 1 atmosphere and 0 degrees? We call that, okay, that was sad. What do we call it when we're at 1 atmosphere and 0 degrees Celsius? S. What do we call it? Okay, I heard like maybe 4 or 5 people. What do we call it when we're at 1 atmosphere and 0 degrees Celsius? S.T.P, what are we at? What are we at? Are you guys that scared of saying 3 letters in a row? What are we at? S.T.P, and what is standard temperature? What is the standard temperature? 0 degrees, and what is standard pressure? 1 atmosphere. Remember, if you say it, it activates the hearing neurons, it activates the speaking neurons. You are more likely to remember it than if you just write it down and read it. So like, get over it. And like, nobody is listening to you specifically saying 3 letters. I guarantee it. Okay, S.T.P. All right, and we have 22.4 liters for each of these. And each of these contains 6.02 times 10 to the 23 molecules, which is how much? What's 1 mole? So all of this that we have been talking about up till this point has been to get us to the point where we can understand that we have found another conversion factor. For gases at S.T.P, what can we convert? We can convert between the volume and the moles because it is always the same, okay? The ratio between volume and moles at standard temperature and pressure is always 1 mole for every 22.4 liters, okay? So 1 mole at S.T.P occupies 22.4 liters. And so now we have our molar volume of a gas, and this is a conversion factor, okay? Isn't that lovely? Now, the question should always say gas. Technically, the question should also say at S.T.P. I feel like there might still be a couple questions in there where I forgot to write at S.T.P. If you find them, let me know so I can correct it. Okay. But let's try this example. What is the volume in liters of a 2 mole sample of methane, CH4, at S.T.P? What is our new conversion factor? 22.4 liters equals 1 mole. Now, don't think that it is 1 liter equals 22.4 moles because that would be wrong. Remember, what does the 1 go with? The 1 goes with the mole. The 1 goes with the mole. Okay, so for molar mass, for Avogadro's number, for this molar volume, the molar volume is the volume of 1 mole. Remember, the molar mass was the mass of 1 mole. So we want to find the volume in liters of a 2 mole sample. So we are starting with 2.00 moles, and we want to find the liters, and we are told this is at S.T.P. Even though it doesn't say gas, if it says at S.T.P, you can assume it's a gas. Okay, so 2.00 moles times, what unit do we want on the top? Liters. And what unit do we want on the bottom? Moles. And so what number goes on the top? 22.4. And what number goes on the bottom? 1. And so we end up with 44.8 liters, which makes sense, right? If 1 mole takes up 22.4 liters, then 2 moles will take up 44.8 liters of space, twice as much space. We can use the same conversion factor, but turn it upside down like every conversion factor we know. So we have, I don't know how many moles this time, that is our unknown. Our initial quantity is 5.60 liters. What unit do we want on the bottom this time? Liters. Okay, and on the top we want moles. And I should have said at S.T.P, so I need to change that. Look, already I haven't written it. Silly me. If on this worksheet, you can assume they're all gases at S.T.P, okay? And I will make sure that any quizzes or tests you have, it will say gas at S.T.P, okay? Where does my 22.4 go? Does it go with the mole or does it go with the liter? What goes with the mole? 1. Where does the 22.4 go? 22.4. And you know how what's easy to remember? 2 plus 2 equals 4. So if you're like 20.4, 2 plus 0 doesn't equal 4, right? 2 plus 2 equals 4, so 22.4. All right, we do that math, and I'm going to cheat. That is 0.250. And now you can do some of these questions. Okay, and I will get your quizzes back to you. Maybe just do the odd ones. 1, 3. Well, these are really boring. These are all just moles to liters and liters to moles. Why are there so many? Oh my God. Okay. Do 1, 3, 5, 7, and then we're going to do 11 and 12. Okay, so 1, 3, 5, 7, 11, 12, and I'll get your quiz back to you. Thank you. Oh yeah. Is it this one? Yeah. Help yourself. I will be right with you. This is pages 90. Only homework. Because there is like the quiz, and if somebody did poorly on the quiz, I want them to have time to review. If we say quizzes are 10%, have we done at least 10 quizzes? Yes. Okay. So each quiz then, if you've only done 10 quizzes, if you've done more than 10 quizzes, each quiz would be worth 1%. Okay. And okay, so we have 1 out of 24. 0.04. But yeah, so if you change the grade by hang on. 1 divided by 24 equals, and then it's 10%, so times 0.1. So if we change your grade, there we go, okay? And then we divide by 10, get 0.16, which is 4%. You know what you're doing. Just sort out your secrets. Okay, don't make me. Do you know how I use my mark? Right? Why would you do that to me for that, which has to be in scientific notation? It's only so small. Right? Okay. Okay. Redoing this is more for people who didn't understand things the first time. You didn't understand what you're doing. Okay. And it's a good exercise for you to learn to let things go when they don't really matter. Because I love it. Just a tiny bit. So this is like a baby step towards letting things go. Okay. Yeah. Grace it, and I don't know why. I don't know. Maybe you rounded up and you didn't care. Now, I haven't printed it out yet, so I have to press print. Stop.